In the previous videos, we used the assumption of the average value. Like, we knew what the average value was. Like, where does the average value come from? Like, why is it defined as if you take the n data points and divide by the total number of data points, that gives you the average value? Like, is it that intuitive? You know, was that the first thing that someone thought of when coming up with the average value? So basically this idea comes back to linear regression, and this is a basic, very, very basic form of linear regression. And if you could extrapolate this idea or this process in this video and apply it to different forms of linear regression. But don't worry, we'll get to at least 3 or 4 types of linear regression and how you could apply that to different forms of data points. But to get started, we're going to look at the very, very simple idea of linear regression. So, in the previous videos, we've been talking about the sum of squares, and the reason why we use the sum of squares instead of just the regular sum of deviations, because it becomes trivial because they add up to 0 and so forth. So what we're going to do, we're going to take n data points. So we're going to define n data points as x1, y1, x2, y2, all the way to xn, yn. And what we're going to do, we're going to plot this on the xy plane because this is a two-dimensional set of data points. So I'm going to plot those arbitrary points as we did in previous videos. So that is our set of data points, and a typical thing to ask is, what is the middle point? So let's say we don't know what x bar, or the average value in x, in the x set of points. We're gonna say, oh, it looks like it's around here. Alright, and we're gonna define that as a, because we don't know this is the average value yet. We don't know that definition. So we're going to define this line as A. And then we could do the same thing for Y. It doesn't really matter which direction we choose. But we know it's just a line, horizontal or vertical. So we could define this as B if you want. But we're going to just look at the average value in the X direction. So we're just going to look at A. And we know the equation of this line. It's simply X equals A. So that's kind of important to know. So we're going to define this line right here as x equals a. And what we want to do, we're going to take an arbitrary point, let's say this point, and we're going to look at the deviations from that point. So this will be dx, and then this will be dy. And this point right here we'll define as xi, yi. So we're going to take that arbitrary point and add the deviations together. But as we figured out, we get a trivial result when adding the deviations. So what instead we're going to look at is the sum of squares. So we're going to define the error in this equation, or an error of this deviation, or whatever you want to call it. We're going to define it as E equals the sum of xi minus a, and square it. That way we don't get a trivial result, or in a way that we don't get errors that cancel out each other. So we're going to look at this equation, and we want to optimize the line, or the average value, since we know it's the average value. That's what we defined it as, but we also don't know it if we were coming up with this definition. So we want to add up the sum of deviations, square them, and find what that is. But we don't know what a is, so we're trying to find a. So what we want to do is optimize this equation to find this line. So what we're going to do is we're going to differentiate with respect to a in this equation and set it equal to 0. That's just the basic concept of optimization that you learned in calculus. And we're going to solve for a. So we're going to take the derivative of e with respect to a, and we're going to set that equal to 0. So if we have the equation DE equals the sum of xi minus a squared. We simply just use the power rule and find this derivative. So DE with respect to a is simply -2 by using the chain rule, xi minus a, and we're going to set that equal to 0. And as you can see, -2 is a constant, and it doesn't conflict with our equation. It doesn't change it. It's on a variable. It doesn't get iterated, so we can move that out of the sigma notation. So we get -2 xi minus a equals 0. So we can divide by -2, and now we get this summation. So as before, we're going to distribute the sigma notation and find a. So we could do the sum of xi minus the sum of a. Since we know a is a constant, we can move it out of the sigma notation as we've done before. So we can rewrite the following equation as xi minus a times sigma equals n. And as before, the sigma by itself is simply the iteration times the value, or times the coefficient. So we have this as xi minus a times n equals 0. So now we can move this to the other side and solve for a. So we get the sum of xi equals an, and then a is simply xi divided by n. So that is where the average value comes from. It is the equation of a line that gives you the minimal amount of deviations. The minimum value of the squared deviations. If you take the sum of the squared deviations, you get the smallest value that you can get if you take the sum. So that's where the definition of the average value comes from. And this is a very basic idea of, linear regression. If you want to find maybe a line, a linear equation, such that it goes through these data points, you could apply the same concept by using this process, which is what we're going to go through in the future. And now we're going to introduce new notations of average values. So, as you have seen earlier in my videos, that we could write a equals x bar, which is the average value of xi divided by n, and then we could say b is the average value, y bar, is the sum of yi over n. And these are the main ideas of average values. So if you take, again, I'm going to quickly go over this. So if you take the sum of all the deviations, they're going to become the square deviations. You're going to get a minimal value, and that's going to determine the equation of the line that you plot. So this becomes like your middle point of or the middle line of your data points. And a very important thing to point out is that we're going to look at this point right here. So this right here, I'm going to move this out, as x bar, y bar. And later this becomes a very crucial point when performing some linear regression. So if you want to plot the line that goes through the data points that is minimal, so let's say we want the deviation of this line, or this point to this line. If we take that sum, this point is a solution to that best fit line. And I'm assuming the intercept is at y equals 0, so I'm not sure if that's true, but given that this is a point, we could say that is a solution to the best fit line, or the linear regression line, which is important to note. So that was this is the beginning of linear regression, and hopefully you guys get the basic concept of where the average comes from and how this concept can be applied to non-constant equations, so such as a linear equation, or maybe even a quadratic equation, or maybe a an equation that deals with three-dimensional data points, and so forth. But that is where the average value comes from.